Welcome back to the Deep Dive. Today, we're moving past some of the more general concepts, and we're
Yeah,
getting into the razor-sharp, highly specific world of precision metalworking.
that's right.
We are diving deep into parting and grooving two operations that, they look deceptively simple, but are, and I don't think this is an exaggeration, the source of some of the most critical and honestly, potentially catastrophic challenges in the entire realm of turning.
That's absolutely right. I mean, this isn't your basic turning operation. This is a very specialized category, and it requires engineers and machinists to really adhere to strict technical methodologies.
The margins for error are just that small.
They're tiny. And the consequences of failure, I'm talking tool breakdown, vibrations, scrapped parts, they're not gradual, they are instant.
Our mission today is to take the technical manuals, the engineering blueprints that professionals rely on, and synthesize them into a clear, actionable knowledge base for you, the learner. We're going way beyond just definitions. We need to understand the mandatory rules that govern system selection, the almost counterintuitive physics of the center cut, and the complex trade-offs you have to make when you're choosing the perfect tool geometry.
And we're going to equip you with the full production planning blueprint. We'll show how experts move from, analyzing the raw material all the way to troubleshooting wear patterns on an insert.
So we're really focusing on those critical factors that determine success or failure when you are machining in a narrow, confined space.
That's the whole game right there.
Okay, so let's start where failure so often originates, the chip itself. In, say, wide-open turning, the chip just kind of flies away. No big deal.
Right.
But in parting and grooving, the primary engineering challenge seems to be just managing the debris that you're creating.
The term we use is chip evacuation, and you've hit on it. It is the single most critical factor in these operations. You have to visualize the process. The tool is moving deeper and deeper into the workpiece, and it's creating a slot. Now, as that slot gets deeper, the space available for the chip, that ribbon of removed material to escape, becomes severely, severely confined.
It's like trying to snake a constantly growing garden hose out of a pipe that's actually shrinking.
That's a perfect analogy. Unlike, say, contouring, where the chip has basically 360 degrees of clearance to just curl up and fall away, here the chip is trapped. It's in a channel, and the walls of that channel are defined by the cut itself.
So it has nowhere to go.
Exactly. And when that chip evacuation fails, you face two inevitable and pretty nasty consequences. The first is what we call chip obstruction.
And that just means the chips are rubbing where they shouldn't be.
Precisely. They're rubbing against the workpiece, they're rubbing against the tool flanks, and that immediately ruins the surface quality of the groove you're trying to cut. But the second one, that's the truly catastrophic outcome. That's chip jamming.
Describe chip jamming for us. What does that actually look like on the machine?
Chip jamming is when that chip literally packs itself so tightly into that confined space that it stops everything. The forces generated aren't gradual, they're instantaneous.
Wow.
The heat just spikes, the cutting force multiplies exponentially, and what you get is an immediate catastrophic tool breakdown. The insert shears right off, the holder can deflect or even bend, and that expensive component you were working on is completely ruined.
So we're talking about a split-second failure.
Split-second failure, all because the force has nowhere to go. It's all contained in that tiny groove.
So, okay, the geometry of the tool isn't just about slicing the metal. It's about forcing the material to become manageable debris.
That is the perfect way to put it. The cutting edge is an extremely sophisticated piece of really microengineering. It's designed to form the chip in a very, very specific way.
And what does a good chip look like in this environment?
A successful chip is typically clock spring shaped, but here is the critical role, the part that's so clever. The insert geometry must actively compress and shrink the chip's width.
So the chip has to be narrower than the groove it just came out of.
It must be narrower. If the chip is the full width of the groove, it simply cannot escape. The dedicated chip breaker geometries, those little bumps and grooves on the insert's shoulder, they exist for one reason only, to achieve that lateral compression and control.
The tool literally has to engineer its own escape route, and the debris has to fit through the exit door that it just created.
And if the physics fail at that tiny scale...
The whole operation is a failure.
Exactly.
All right, let's move from the geometry to the movement, the kinematics.
Yeah.
This is where the math starts imposing some really non-negotiable rules. So for the learner, let's quickly define our key terms. We've got spindle speed, which is N.
Right, and RPM.
Cutting speed, VC. Radial cutting feed, which is FX. And of course, the tool overhang, OH. Now, in general turning, VC might stay pretty constant, but in parting off, we hit what the technical manuals call the centerline problem.
And this is the defining difference, the thing that separates general turning from parting off. It's essential to understand the physics here. Your cutting speed, VC, is a function of the rotation speed, your N, and the current diameter you're cutting at, D.
So as you cut inward, as you part off a piece, that diameter D is constantly shrinking.
Constantly shrinking, which
The
means
cutting speed plummets.
it absolutely plummets.
Okay.
Even if your machine is set to maintain a constant surface speed, it will eventually hit its maximum spindle RPM limit. It just can't spin any faster.
Right.
And once that limit is hit, the cutting speed, VC, must decline dramatically as the diameter approaches zero. And this drop causes a profound force imbalance.
What does that feel like in the cut?
The forces acting on the tool become unstable, friction increases, and vibration increases exponentially. You get chatter. The material is no longer being efficiently cut. It's being, well, rubbed and torn, which generates a massive amount of localized heat.
So the key has to be intervention. You can't just let the machine coast to the center and hope for the best. How do professional machinists counteract this sudden shift in force dynamics and heat?
By enforcing a mandatory feed rate reduction, it's not optional. You start the cut with your optimal radial cutting feed, FNX, but to preserve stability and keep the cutting force predictable as that VC vanishes, you must reduce the feed rate significantly.
And the technical sources, they're unyielding on this point.
It's a non-negotiable law of the process. You have to do it.
Okay, so what are the specifics of this precision rule? We need the numbers.
The feed rate must be reduced down to the minimum recommended, or more specifically to 0.05 millimeters per revolution.
0.05.
That's just 2/1000ths of an inch per revolution.
That is.
It's essentially slowing the engagement to a crawl to manage that final, delicate separation of the part.
And timing is everything here. When do you hit the brakes on the feed rate?
The reduction has to begin exactly 2 millimeters, that's less than 1/10 of an inch, about 0.079 inches, before the tool reaches the center line of the part.
So in that little 2 millimeter buffer zone, that's where all the instability happens.
That's the transition zone. It's where the forces go from stable cutting to highly unstable rubbing.
Wow. Okay, so 2 millimeters out, you might reduce your feed rate by, what, 80 or 90%? That level of control is just astonishing. What happens if a machinist ignores this tiny but precise rule?
If you ignore it, you're asking for trouble. You risk plastic deformation of the insert from the heat, you'll get massive chatter, and I can almost guarantee premature tool failure.
And what about the part itself?
Well, practically, and maybe more importantly for production, the cut will leave a large jagged remnant in the center. We call it the pip.
The pip.
Right. And adhering to this rule, this feed reduction, dramatically increases your tool life, it stabilizes the cut, and critically, it minimizes that final pip size. That ensures a cleaner component that doesn't need costly secondary finishing.
So that one tiny rule, 0.05 millirev starting 2 millimeters out, is really a hallmark of professional high-volume parting.
It absolutely separates the amateur cuts from the efficient, mass-produced results.
Now let's transition smoothly to the other main application here. Grooving and face grooving. How does the terminology and the geometry differ?
Well, in grooving, we introduce the concept of an axial feed, which we call M&Zs. That means we might be moving the tool along the length of the part, not just radially toward the center. We also define the depth of the groove, which is R.
So grooving is often a multi-directional operation. You're going in and then sideways.
Exactly. It involves both radial FNZs and axial FNZs movement.
And face grooving, that's cutting a groove into the face of the component, essentially machining a radial slot.
Right. And face grooving really mirrors the centerline problem we just talked about because you are still feeding radially towards the center using a FN6.
So the machine will follow the same pattern.
The exact same pattern. It will increase RPM until it hits its limit, and then the cutting speed, VC, will drop to 0 at the center. The methodology for feed reduction is often very similar, though the tool geometry is a bit different. It's designed to direct chips out of the face groove, which is usually a little less confined than a deep parting operation.
So regardless of the specific application, it sounds like the feed rate, FN, is the central control lever for the machinist.
It is the absolute dictator of the process. I can't stress that enough. The feed rate governs how the chip forms, whether the chip has enough stress built into it to break cleanly, the thickness of that chip, and vitally, how the chip interacts with the insert's geometry.
And when you're using the tool for sideways turning for profiling.
Well, then the depth of cut app also plays a massive role in chip formation. You often need to make adjustments to your feed rate to ensure that chip is still curling and breaking correctly, even when you're moving axially.
Okay, this brings us to the bigger picture. The sources outline a really systematic 5-step planning process for approaching any new job in this category. It's like the professional's roadmap for avoiding costly errors.
It is. That roadmap ensures that no critical variable is overlooked. It's very logical. Step 1, analyze the component and the workpiece material.
Okay.
Step 2, review your machine parameters. Step 3, choose the right tool and, importantly, the right machining method. Step 4 is determining the application, your feeds, speeds, your coolant strategy. And finally, step 5, prepare for troubleshooting. You always plan for things to go wrong.
Let's start with steps 1 and 2 then. Analyzing the job requirements and the capabilities of the machine you have.
Right. When you're analyzing the component, you're looking at the finish requirements. What's the cutting depth, the width? What's the critical corner radius? What are the overall quality demands?
And the material itself.
Then you look at the material, its machinability, its hardness, its alloy elements. But for this specific operation, the most important material characteristic you need to consider is its chip breaking capability.
So if you have a material that tends to form long, stringy chips.
Like some stainless steels or low-carbon steels.
Right.
You know immediately that your tool geometry and your feed rate have to be extremely aggressive to force that chip to break. You can't be gentle with it.
And the machine itself, it imposes some significant constraints. It's not just about horsepower, is it?
Oh, it's far more subtle than that. Machine stability is paramount. It's tied directly to the rigidity of the entire setup. For parting off a large diameter part, for instance, you need tremendous power and torque just to start and sustain the cut, especially on tough materials.
And the clamping of the part.
Crucial. You have to analyze the component clamping rigidity. If that part moves even microscopically during the cut is ruined. The surface finish will be terrible. Dimensions will be off. And finally, we look at the turret interface and, critically, the chip evacuation and cutting fluid systems on the machine.
You mentioned the cutting fluid system as a constraint. Why would a good system be a prerequisite for, say, deep grooving?
Because without high volume, precision coolant directed exactly at the cutting edge, deep grooving is almost impossible. The heat and the friction that are generated in that confined space are immense.
So if the machine can't deliver the fluid precisely?
Then you simply cannot run at the optimal feeds and speeds. You have to slow everything down, which immediately limits your productivity. You're leaving money on the table.
Okay, that sets the stage perfectly for step 3, choosing the right machining method. This is where strategy really trumps brute force. For roughing out a wide groove, the decision depends entirely on the ratio of depth to width.
This is a classic engineering problem where you choose a strategy based on the geometry of the feature. So if you have a rough grooving job where the depth is bigger than the width, think a deep, narrow slot. The superior method is something called multiple grooving.
Explain the mechanism behind that. What does it mean to make a fork?
So instead of just plunging the full width of the groove in one go, you use a series of narrower cuts and you leave little slivers of material or forks between them.
And the advantage there is?
It's twofold. First, the successive cuts are removing material that has already been stress relieved by the previous pass, so it's easier to cut. Second, and this is the clever part, the chips generated by the subsequent cuts are broken against the existing relieved faces of that fork structure.
Ah, so you're using the workpiece itself as a chip breaker.
You are. This mechanical action drastically improves chip flow, it prevents jamming, and it significantly extends tool life because you're managing the force distribution much more effectively.
Okay, so what if the constraints are reversed? The width of the grooves is larger than the depth.
Yeah.
A wide, shallow slot.
Then the optimal choice is plunge turning. This is really favored, especially for machining steel and stainless steel, because the stability of the tool is maximized when the forces are primarily axial or vertical relative to the tool holder. And plunge turning inherently gives you excellent chip control when the width allows that chip to move freely from side to side.
And the third major method is ramping. Now, this one sounds inherently inefficient, almost counterintuitive.
Ramping is the strategic choice when you absolutely must prioritize stability and minimize radial forces and vibration. It involves using strong, typically round inserts and feeding the tool gradually along a path, spreading the stress over a larger arc of the cutting edge.
But ramping inherently requires doubling the number of passes or cuts, which costs time. Why is that sacrifice worth it?
It's worth it because ramping is the first choice for machining heat-resistant superalloys, your HRSAs, like Inconel or Hastelloy.
Right, the really tough, gummy materials.
Incredibly abrasive, and they're prone to work hardening. The primary failure mode in these alloys is notch wear. That's where the tool breaks down right at the corner, often due to concentrated thermal stress.
And ramping helps with that.
By ramping, we distribute that thermal load across a much longer segment of the round insert. We're avoiding that single point of stress concentration. So yes, you trade cycle time, but in return you get guaranteed tool integrity and component quality, which is a trade you'll make every time on a $100,000 part.
Okay, now let's look at the sheer variety of applications that fall under this category. This tool map in the source material really illustrates the precision required across a whole range of scale demands.
It does. I mean, we're talking parting off solid bars, shallow grooving, deep grooving, profiling, undercutting. It's a huge family of operations.
And the source material gives very specific examples of diameter and depth ranges, which I think drives home the necessity of really customized tool selection.
Yes. For your external operations, the scale dictates the system you choose. Shallow parting might cover diameters less than 12 millimeters, which is a relatively simple operation.
But deep parting,
Deep parting can cover diameters up to 160 millimeters. That requires heavy, often damped tooling to manage the forces and vibration. Shallow grooving might only go 3.7 millimeters deep, while deep grooving can extend over 100 millimeters. You have to select a system that's designed for that specific reach and force level.
and then when we move the operation to the inside of the component for internal machining, the constraints just multiply, don't they? Primarily around accessibility.
The problem immediately shifts from tool rigidity to tool size. You are completely constrained by the minimum hole diameter. For example, if you're performing internal circlip grooving using the smaller carbide rod inserts, the absolute minimum hole diameter you can work in is 4.2 millimeters. That's tiny.
And if the hole is smaller than that,
The operation can't be done with that specific system. The geometry of the part itself dictates your tool choice. The moment you move inside a part, the rigidity conversation becomes infinitely more difficult.
which brings us directly to the core engineering tension in this entire discussion, the battle between stability and accessibility.
Yeah.
And the fundamental rule is always crystal clear. Minimize your tool overhang, your OAs.
Always. That is the foundational law of stability in machining. The tool overhang must be the shortest possible distance required to reach the cut, and you must use the largest seat size and holder height possible because stiffness is proportional to the cube of the holder height. You have to maximize stiffness and minimize OH.
But as we just established, in deep parting or internal grooving, accessibility requires a long reach, which inherently compromises that stability. This is the compromise you are forced to make every time.
It is the central conflict. And to resolve this, engineers have to strategically choose the material of the toolbar itself. The technical manual provides hard limits for the maximum recommended overhang relative to the diameter of the machine mount, the DMM, or shank size.
Let's detail these solutions because this is where technology really starts to solve the physics problem.
Okay, so if you are using standard solid steel bars, your overhang limit is severe. You can only go up to 3 times the DMM. That's it.
3 times the shank diameter.
Right. If you need more reach, you have to upgrade. Moving to dampened steel bars or solid carbide bars allows you to stretch that to 5 times the DMM.
Okay, that's a significant jump.
It is. But for maximum reach, particularly in those really challenging internal or deep cuts, you use a carbide reinforced dampened bar that allows an overhang of up to 7 times the DMM.
Wait, let me just absorb that for a second. By upgrading the material of the tool holder, you can essentially buy almost 4 times the practical reach, going from 3x DMM to 7x DMM while maintaining the necessary stability.
That is a massive technological leap, and it exists purely to solve that accessibility problem.
How does it work?
It's all material science. The carbide component provides a much higher modulus of elasticity. That just means it resists bending and vibrations significantly better than steel. It allows you to, in effect, cheat the physical laws of cantilevered loads.
Okay, so let's look at the tool holder itself, the component that physically grips the insert. The choice here seems to be driven by application and priorities.
Yeah.
Is it speed of change, or is it ultimate rigidity?
Exactly. For deep parting, where you're frequently cutting off large diameters and you need to index your inserts fast, the first choice is usually a spring clamp blade system with single edge inserts. They're quick, they're efficient, and they often allow for easy tool block adjustment to fine-tune that critical overhang.
But if the focus shifts to pure grooving, where you're dealing with those multi-directional forces, FNX and FNZ, then rigidity becomes king.
Absolutely. For rigidity and precision, you're going to choose screw clamp and spring lock designs. These clamp the insert much more firmly in place, minimizing any micromovement during the cut, and they usually offer the best path for precision coolant delivery directly to the cutting zone.
And then there's the pragmatic, economic choice for mass production.
Right. That's the screw clamp holder designed for 3-edge inserts. The economic benefit is obvious. You get 3 cutting edges per insert, so your cost per edge goes way down.
But it's more than just cost, right?
It is. Crucially, these systems allow for extremely narrow cuts. You can groove down to 0.5 millimeters wide and part down to 1 millimeter wide. This ability to use the narrowest possible insert not only minimizes your cutting forces, but also saves a substantial amount of material over thousands of parts.
Which is a major financial and environmental benefit.
A huge benefit.
All right, let's reiterate what seems to be the most unforgiving setup rule in all of parting off. Center height precision.
The source material is so demanding here. The maximum deviation from the center line is only plus or minus 0.1 millimeters.
That's 0.004 of an inch total. That is an incredibly tight window for error.
And the consequences for missing that tiny window are severe. If your cutting edge is too high, the necessary clearance angle on the bottom of the insert just disappears. The tool starts rubbing aggressively instead of cutting, which generates friction and heat and leads to immediate fracture.
And if it's too low?
Conversely, if the edge is too low, the tool physically cannot cut the material cleanly at the center line. It leaves behind that dreaded PIP, the little burr or remnant of material.
And the pip is more than just an aesthetic issue, isn't it? It's a costly problem.
It's a production killer. If that pip is large enough, it can prevent the part from seating correctly in a subsequent machine setup, or it might require a secondary manual operation like grinding or filing just to remove it.
And that manual step just wipes out all the efficiency you gained in the automated turning process.
Completely. That tiny 0.2 millimeter window of precision isn't just a technical goal, it's a financial necessity.
We mentioned using the narrowest possible insert width earlier. Beyond the cutting force benefits, the material savings must be pretty substantial in high-volume production.
They are enormous. Think about it. Every millimeter of width you save translates directly into less material being wasted as swarf, and therefore less pollution and lower material costs. It's a very small change that has a huge macroeconomic and environmental impact over a production run.
Now for another classic trade-off in insert geometry, the corner radius. You have to decide between maximizing your stability and minimizing that final burr.
This choice really balances control against longevity. A small corner radius is what you choose when you need a very small final pip, exceptional chip control, and high precision.
But the downside?
The downside is you have to run at a lower feed rate, so you're sacrificing cycle time. That small radius is just more delicate.
And the large radius?
The large corner radius allows for a significantly increased feed rate, which boosts productivity, and it drastically improves tool life by strengthening the tip. But you trade off some of that fine chip control, and the final pip left on the component will inevitably be a little bit larger. It's a calculated decision based on the required finish quality versus the production volume you need to hit.
Okay, let's discuss how the tool's entrance angle fundamentally dictates chip flow and burr control. The default choice is the neutral entering angle.
Right, the neutral entering angle is preferred because it maximizes the strength of the cutting tip. That strength allows for higher feed rates, you get a better surface finish, and a straighter cut. And crucially, a neutral angle directs the chip straight out of the groove, which maximizes that necessary chip control we spent so long talking about.
But there's a drawback.
The drawback is that the resulting tip generally stays on the component as it separates from the bar.
But then we have the strategy of using front-angled inserts, left or right hand, specifically to control that final pip. Wait a minute. We spent an entire section emphasizing that chip control is life and death in this operation, and now you're telling me professionals will intentionally sacrifice it just to fix a burr. That seems like a huge risk.
It is a calculated risk, and you've really hit on the core tension. A front-angled insert works by changing the way the final material separates, which reduces the size of the pip or the burr left behind.
But the caveat is huge.
The caveat is, as the source material notes, that using this angled approach reduces chip control. It does this because it changes the direction of the chip flow, preventing that clean, straight evacuation we want.
So why on earth would you take that risk?
You take the risk when the cost of pip removal, that secondary operation, outweighs the risk of catastrophic chip jamming. And you can usually mitigate that risk by adjusting your feeds and speeds or increasing your coolant flow. If you are producing millions of components where the pip absolutely must be minimized for, say, automated assembly, then the front angle geometry becomes essential despite that inherent compromise in chip management.
So it's a purposeful sacrifice of microcontrol for a guaranteed macro component quality.
That's a great way to put it.
And finally, we have to return to the role of precision coolant. You've said it a few times, but it seems like it cannot be overstated.
It really can't. It's necessary because that restricted space is so often obstructed by chips.
It's not just for cooling then.
No, it's essential. The requirement is to use cutting fluid in large amounts and directed precisely at the cutting edge. That's what we mean by precision coolant delivery. And it has to be on throughout the entire operation.
So what's it doing besides managing temperature?
It's providing hydraulic assistance to literally push those chips out. It prevents jamming, it improves chip formation by reducing friction at the cutting edge, and it measurably extends tool life. It's the lubricant, the thermal manager, and the chip ejector all in one package.
All right, let's move into some of the more specialized applications, kicking off with general grooving. Single-cut grooving seems to be the economic baseline. But what happens when the demand for the quality of that groove goes up?
If high quality is paramount, the machinist is going to move away from standard geometry and choose one of two specialized solutions. First, there's a finishing geometry.
And that's just a more precise insert.
Exactly. It's designed with an ultra-tight width tolerance, usually plus or minus 0.02 millimeters, just to ensure the groove width is exactly correct. The second option is wiper inserts.
What exactly is a wiper insert doing in this context?
So, wiper geometry features a secondary, wider flat section on the cutting edge. Its purpose is to machine the sidewall of the groove, generating an extremely high surface quality on the groove sidewalls. If you need a near-mirror finish on the sides of your groove, the wiper is the way to go.
And circlip grooving is a frequent requirement in automotive and aerospace parts.
It's a very standard operation. It can be performed with both 3-edge or 2-edge inserts. But again, for internal circlip grooving, the critical constraint is always the hole size.
Back to the 4.2 millimeter limit.
Right. Using those carbide rod inserts for this task limits you to a minimum hole diameter of 4.2 millimeters. If the hole is any smaller, the operation simply cannot be done with that specific system. The geometry of the part dictates everything.
Now, face grooving, cutting a groove into the face of a component. This requires dedicated tools that actually follow the curve of the workpiece.
Yes, the tool holder itself must be curved correctly to match the radius you are machining. But the methodology here is absolutely key for success. You must always machine the largest diameter first and then work your way inwards.
Why start wide and move in? What's the logic there?
It's all for optimal chip control. If you try to machine the inner smaller radius first, the chip that's generated at the outer diameter on your next cut has a much higher likelihood of clogging up that intersection you just machined.
Ah, so you're creating clearance for yourself.
Exactly. By starting at the largest diameter, you create the maximum clearance available for the subsequent chips to escape easily as you move inward. And furthermore, your roughing cuts, say cuts 2 and 3, should only be about 0.5 to 0.8 times the insert width. That conservative cut ensures you get acceptable chip breaking before you go in to finish the final groove dimensions.
Moving beyond straight grooves, we need to talk about complex profiling and turning with these specialized systems.
Right. When you're machining complex radii and profiles, modern grooving systems will use round inserts as the first choice. They offer really outstanding chip control and deliver a superior surface finish because the contact point is constantly changing and the stress is distributed.
But there's a critical caution in the notes here regarding matching the insert radius to the component radius.
Yes, you should avoid matching the radii if at all possible. It is strongly recommended that the insert radius be smaller than the component radius.
Why is that?
If the radii match, the tool maintains continuous contact over a very large area. That is the perfect recipe for inducing severe vibration and creating a long, stringy, unbroken chip. It's a nightmare scenario for chatter.
And if you are absolutely forced to match the radii for some reason?
If matching is unavoidable, you have to use a programming technique called microstops. These are just momentary interruptions or dwells in the feed rate that physically shorten the chip and interrupt the vibration cycle. It allows the system to kind of reset itself before continuing the profile.
What about using these systems for more standard turning applications like roughing and finishing wide grooves?
For roughing wide grooves, the technique is very precise. You radially infeed to your target depth plus an extra 0.2 millimeters. Then you turn axially until you reach the opposite shoulder and you retract.
Why the extra 0.2 millimeters?
You need that extra radial cut to ensure you clear the shoulder properly on your axial pass. Now for finishing, the secret weapon is what we call the wiper effect.
Tell us more about the wiper effect. That sounds like a high-end technique.
It is. The wiper effect uses very shallow axial and radial cutting depths, typically between 0.5 and 1.0 millimeters. This shallow cut, combined with a slightly wider geometry on the insert, creates a controlled wiping or burnishing action. This action significantly improves the surface quality.
How good are we talking?
We're talking about generating an ARA, or a roughness average, value below 0.5 micrometers.
For context, a ray of 2.5 is an extremely fine, smooth surface that's often required for sealing surfaces or bearing fits. How is that level of quality even achieved?
It's achieved by finding the perfect synergistic combination of the feed rate and the subtle, controlled deflection of the tool blade itself. The blade is designed to give just slightly under load, and that shallow cut utilizes that micro-deflection to generate that final, polished surface. It's very clever.
And finally, undercutting creating clearance for threads or other features.
Undercutting demands dedicated, sharp, and highly accurate inserts. They often have tight width tolerances of plus or minus 0.02 millimeter. And these inserts are usually angled 7, 45, or 70 degrees to provide the necessary clearance to complete the feature without rubbing on the shoulder.
Okay, we've planned the cut. Now, the unavoidable reality. Troubleshooting. The ability to diagnose tool wear is absolutely essential for minimizing downtime. Let's break down the common wear patterns and what they're telling us.
The machine tells you a story through the failure of the insert. If you see chipping or fracture, it means the tool is simply too weak or brittle for the forces you're applying. The solution: use a stronger, tougher carbide grade or immediately reduce your feed rate.
What if the wear is more gradual, like flank wear? Just wear on the side of the insert.
That indicates simple abrasion. The standard fix there is to increase your cutting speed, which often allows the material to shear more cleanly, or you can switch to a more wear-resistant grade of carbide. If you see crater wear, a dip forming on the top face of the insert, that's a sign of excessive heat and a chemical reaction with the chip.
So you need to cool it down.
Exactly. You need to decrease the cutting speed or choose a grade that is more thermally resistant.
Let's discuss the really heat-related failures, like plastic deformation or build-up edge, which is BUE.
Plastic deformation is literally the insert melting or deforming under heat and pressure. It requires a tougher grade of carbide that can withstand higher temperatures, or, most commonly, you just need to decrease the cutting speed to reduce that thermal load.
Again, built-up edge.
BUE is when the workpiece material welds itself onto the cutting edge. This is really common in sticky materials like stainless steel or aluminum.
How do you fight BUE? It seems like it would just get worse.
You fight BUE by actually increasing the cutting speed, making the material too hot to stick, or by using a more positive, sharper geometry that cleanly shears the material before it has a chance to adhere.
Now, for production problems that aren't strictly wear-related, let's say you're getting bad surface quality.
This is almost always a stability issue or an evacuation issue, so the checklist is rigorous. Use the shortest, most stable tool setup you can. Verify that critical center height is within that plus or minus 0.1 millimeter window. Change the geometry if you need to, and ensure your precision coolant is flowing correctly.
And there's a specific fix for aluminum.
Yes. If you are specifically cutting aluminum and the surface is bad, the non-negotiable fix is selecting the sharpest geometry possible and utilizing a specialized soluble oil. Standard coolants often aren't formulated to prevent adherence on aluminum.
And if the core failure is bad chip breaking, what's the immediate strategy?
If your chips aren't breaking, you need more aggression or some kind of interruption. The solutions include selecting a significantly higher feed rate to increase the chip's thickness and force it to break. You can also use dwelling or pecking motions in your programming to physically interrupt the chip formation. And, as always, check that your geometry is optimized for chip control and ensure your precision coolant is flowing.
And the dreaded vibration. the universal machinist headache.
Vibration just screams instability. The core fixes are always structural. You have to ensure the most stable setup possible, check your center height and angles, and critically minimize the overhang for both the tool and the component itself.
What if the tool life is just poor, even without obvious wear signs?
Then you need to check the condition of the tool blade holder. An old or worn holder won't clamp the insert securely, which leads to microvibrations and instability, and that will cause premature failure of the insert every time.
It really is a systemic problem. Every single element, the holder, the insert, the coolant, the feed rate, it all has to align perfectly within these tiny, tiny tolerances.
It's a chain, and it's only as strong as its weakest link.
This deep dive has really underscored that parting and grooving are not simple cuts. They are highly engineered operations governed by ironclad physical laws, and they're primarily dominated by that absolute necessity of aggressive chip evacuation in these confined spaces.
And we established the mandatory rules governing feeds. That precise, unforgiving reduction to 0.05 millimeters per revolution, starting just 2 millimeters before the center line. That is the hallmark of a professional operation. We also saw that every tooling decision involves a critical trade-off.
Right. A small corner radius gives you control but sacrifices tool life. A front-angled insert controls the burr but sacrifices chip evacuation.
There's no free lunch.
So the ultimate takeaway for you, the learner, is that mastering this domain requires respecting the smallest details. We're dealing with setup tolerances measured in hundredths of a millimeter. Success isn't about power. It's about the systemic alignment of the material, the machine's rigidity, and the chosen methodology.
And this brings us back full circle to that foundational design tension we identified right at the beginning, the stability versus accessibility compromise. When you're performing deep internal grooving, you are forced to use a long tool. That necessitates a long overhang, an OH, which inherently sacrifices your stability.
The engineering problem, then, is how do you overcome the laws of physics to get the necessary reach without everything shaking apart?
And the solution lies in advanced tooling. We saw that a standard steel bar limits your reach to 3 times its diameter, 3x DMM, which all but guarantees instability on deep cuts. The technological solution is that carbide-reinforced dampened bar, which allows you to extend that reach up to 7 times the DMM.
That one hardware upgrade fundamentally changes the definition of what is mechanically possible. It just moves the boundary of that trade-off.
Exactly, and the question for the engineer then becomes this. Given the specific depth and size requirements of your component, how much stability are you willing to trade for accessibility? And how does the investment in a carbide-reinforced system fundamentally alter that equation, allowing you to achieve depth and quality that would be physically impossible with standard steel tooling? That balance of risk, reward, and technology, that's the central challenge in advanced turning.